Hello guys, this is Fanta Devs recording on cryptography and number theory. We'll be using Pari calculator, and I'm introducing the first member, Simba Bob, to take us through divisibility.
So I'll be starting with divisibility, and as we know that a number is divisible by another, or A is divisible by B, if there exists a constant K. That we know, and we will be using PariGP, which is a computer algebra system that is geared towards research in number theory. So I'll be starting with, for example, checking the divisibility of a number, like if 4 is divisible by 20. Uh-huh. We will be using modes like modulus. For example, we know that if a number is divisible by the other, there will be no remainder. For example, if we divide 20 by 4, uh, the, the answer is 5, which is a full integer, and there are no reminders. When there is no reminder, or rather when there is a reminder, we will have gone to congruences. So a number is divisible by the other when there is no any reminder. For example, let me start with the 20, or checking if 4 is divisible. For example, I will write in the screen 20 and 4. When you look at the answer, which is mod 0 and 4, it means that the number 20 means that the number 20 has been divided by 4. 20 has been divided by 4, and the remainder is 0. The remainder is 0. So this is the divider, the 4, and it is 0. For example, if we are dividing, let's say 20 by 3, we will get 6 times 3, which is 18, and a remainder of 2. Uh, and as I've illustrated that 20 is divisible by 4 because there is no remainder. Let's do another one for an even. Let's do 21 divided by 5. Then 21 5. As we can see, when 20 is divided by 5, the divider 5, we say that, for example, A is divisible by B modulo N. N is the divisor. If you divide 21 by 5, there is a remainder of 1. 4, let me see, 5 times, and then a remainder of 1.
Thank you very much, Bob. We are glad for your presentation. You have introduced PariGP to us, and you have showed us how to use the mod into divisions and getting a 0 where there is no remainder, and getting a 1 of the remainder where there is a remainder, using the modular division in PariGPT. Thank you for that. Now we are moving to Joseph Muema to take us through congruence. Joseph, kindly share your screen.
Okay, everyone, I'm Joseph. Today I'll be taking you through congruences in number theory and how we can work with them using PariGP. Congruences is a way, we can say that congruences is a way of comparing two numbers based on the remainder when divided by a fixed integer or number, which we call a modulus. For example, we can say A is equals, for example, A is equals to B modulus N, M. This implies that both A and B leave a remainder of M. Both A and B leave a remainder of B
the same remainder
when divided by A and B. So we'll just get straight into the presentation of congruences and how they work in PariGP. In PariGP, we can check if two numbers are congruent by using the modulus operator, which is the manual way of checking if congruency exists. We can use variable A, and assign it a value of 17. And then variable B, assign it a value of 5. And M, assign it a value of 6. So now, when press enter, you'll have to write the function to check for congruency. You'll have to check using the modulus or the modulus operator. So you can say A modulus M so modulus M. And then you hit enter. It will give a value of 1, which this return value indicates that the congruence is true. Alternatively, instead of manually checking for congruences, we can use the modulus function to automatically work with numbers in modular arithmetics. Like, for instance, we can just use mod 17, 6. For those who are using Fedora, if you write mod with a small m, it will give an error because Fedora is case sensitive. So this will give an output of these outputs. This output confirms that 17 is congruent to 5 modulo 6. So I hope we are together till that point. Also, PariGP allows us to perform operations directly in modular arithmetics. For example, a function or operations like addition and subtraction using the modular operators. Like we can have mod and then perform an operation addition. Then we add it to this B and 5. So the result is this mod 0, 0, 5, since 10 is divisible by 5. And then you can also perform multiplication. For instance, you can just repeat this using the same modular operators. You can use mod 4 and 7. And then perform the operation to multiply it with this modular function of mod 3 and 3, 7. Yeah, so it outputs mod 5 and 7. Since 4, if you multiply 4 and 3, you'll get 12, which is equal to 5 and is divisible by 7.
Thank you for your presentation. I now welcome the next member, Kunga Malombe.
Maxwell, my screen is visible?
Yes.
Okay, thank you for that. So my name is Kunga Malombe, and I'm going to take you through list residue. Okay, in number theory, we say like the list residue of an integer, for instance, integer A modulo n is the smallest non-negative integer, for instance, r, such that a is congruent to r modulo n. Now, it's just like it's a reminder when a is divided by n, adjusted to be in the range of something like n, a, and then n to -1. So, for instance, let me take two numbers. A, let me say 17, and then n, I'll say something like 5. When you divide 17 by 5, you'll get 3, but there is a remainder of 2. Now, the least residue is these two of ours. If you get a negative number, for instance, -3, and then n we say 4, we need a negative number, for instance, comma r, where -3 is congruent to r modulo 4. You understand me? Like adding 4 to -3 gives you something like not really something, but it gives you negative, not negative but +1. So the least residue definitely will be 1. Now we can make some computations. Let me start PariGP just that way. So we will have something like okay, our first choice was 17, so we'll go for 17 modulo 5, and we'll get 2. The other one was -3. Then for that we put 4. You see it comes to 1. Like just that's how simple we compute the least residue using the PariGP. I hope the explanation was clear. Yeah, we can also compute it for, let me say, large numbers. For example, you can choose a number like 1, 2, 3, 4, 5, and then we'll choose something like 70. No, let me choose 63. And you see, we'll have a least residue of 60. Yeah. So, any question?
We thank you. We thank you for showing us that. That was been great. Now,
okay,
the last
thank you.
part we haven't discussed is about residue classes, where a residue class is a set of integers that are congruent to each other modulo a certain integer. Let's say that if n is a positive integer, the residue class modulo n are the sets of integers that give the same remainder when divided by n. That's clear to understand, where we say that if n is a positive integer, the residue class modules n are the sets of integers that give the same remainder when divided by n. By using the system, you tackle that and you say that it's simple calculating the residue classes. We thank you for your time. This has been Fanta Devs, courtesy of Kisii University, Software Engineering, 4th year, semester 2, undertaking number theory and cryptography, led by Dr. Maake. We thank you for your time.